Welcome to educator.com. We're in the Calculus 1 sequence, and we're going to take a quick review of functions. So to remind you, a function y equals f of x is a rule that assigns exactly one value y to each value x in the domain of the function. And again, the set of sort of legal x values is called the domain of f. And then the set of y values obtained by those x values is called the range of f. We have the vertical line test that gives us a graphical way to look at whether or not something is a function. And the vertical line test says that a graph describes a function if every vertical line crosses the graph at most once. And so, for example, something like this that I'll draw in a moment would pass the vertical line test. So here's something that is a picture of a function. Notice that any vertical line that I might draw, no matter where I choose to draw it, it would cross the graph at most once. On the other hand, let me draw a second picture. Let me draw an example of something that would not be a function. So for instance, if we had a graph that looked like this, then notice that there are lots of vertical lines that would cross this graph more than once. And so this second picture would not be describing y as a function of x. And for future reference, let me just write that in here, that this second picture is not describing a function. And the first picture that I drew is describing a function. Okay, so let's look at some function examples where I'll provide actual formulas rather than just roughly drawn sketches. So for example, something like y equals x squared would certainly be a function, and its graph is the familiar parabola. And so here's a rough graph of y equals x squared. And of course, notice that every vertical line that I might draw crosses the graph at most once, in this case exactly once. Another example of a function would be y equals natural log of x. And some of these functions we'll look at again later in this tutorial as we look at some other descriptive terms for functions. But here's a rough graph of y equals ln of x. And let me erase that little extra bit that I drew in. And notice that this as well is a function that any vertical line that I might draw is going to cross this graph at most once. And let me just draw in one third one. Suppose we look at y equals e to the opposite of x. Again, it's a familiar graph showing a decaying exponential. So something like this. And again, notice that any vertical line that I might draw would cross this curve at most once, in this case again exactly once. And then just to put up one more example of something that's not describing y as a function of x, if I looked at the equation x squared plus y squared equals 1, this is another familiar graph. It's a circle with radius 1 centered at the origin. It is not a function because, as you can see, there are a number of vertical lines that would cross this graph twice. If we wanted to achieve y as a function of x here, we'd have to do something like, for instance, just selecting the upper half of the circle so that the graph would then pass the vertical line test. Okay, so let's look at some other descriptive terms for functions. We can speak of a function as being an even function or an odd function, and most functions are neither even nor odd. So an even function is a function such that f of the opposite of x equals f of x. And such a function is symmetric about the y-axis, and we'll look at an example of this in just a moment. An odd function is a function for which f of the opposite of x equals opposite of f of x. And such a function is symmetric about the origin. And let me actually put some sample sketches up here, even though we'll look at further examples in a moment. So for an even function, we're speaking of a function that is symmetric about the y-axis. And so an example of that would be this function, where you can see that if you pick any positive value x and look at the corresponding y value, and then pick the corresponding negative value for x and look at its corresponding y value. This is a rough sketch by hand, but I'm trying to indicate that the two corresponding y values would be equal. For an example of an odd function, we could look at something like the following. So let me just draw in a sample odd function. Something like this would be an odd function. So for instance, if I picked some positive x value and looked at f of x, and then picked the corresponding negative x value and looked at f of x, the corresponding y values are opposites of one another. The reason this is called symmetry about the origin is because if I sort of connect a line between these 2 points, that line passes through the origin. For the even functions, when I say they're symmetric about the y-axis, that's simply saying that the graph is a mirror image of itself about the y-axis. Okay, so let's look at some examples of even and odd functions with formulas this time. So for an odd function, one famous example of an odd function would be y equals sine of x. So notice that f of the opposite of x would equal sine of the opposite of x, which equals the opposite of sine of x. For example, if we looked at, let's say, sine of negative pi over 2, so sine of negative 90 degrees, also known as 270 degrees, we would get negative 1 out. Whereas if we looked at sine of pi over 2, we would get positive 1 out. So we threw in opposites of one another for x and obtained opposites of one another for y. And I'm claiming that that's true for every x. The fact that it's true for every x is what makes y equals sine of x an odd function. And if we look at the graph of y equals sine of x, we can confirm that we're dealing with an odd function. And so here is what the graph of sine of x looks like, roughly speaking. And it's an imperfect graph since I drew it by hand here. But the idea is that whatever positive x value I pick, and I look at the corresponding y value, if I were to pick the corresponding value opposite of x and looked at the corresponding y value, those y values are opposites of one another. If I were to connect a line segment between the 2 points, that segment would pass through the origin. For an even function example, we could look at, for example, y equals x to the 6th power. Notice that f of the opposite of x would equal opposite of x all to the 6th power, which is x to the 6th power, which gives us f of x back again. So for all x, f of the opposite of x equals f of x. And just as a numerical example to think through this, if we looked at f of 1 to the 6th power is 1. If we look at f of negative 1 whole thing to the 6th power is 1. And I've thrown in parentheses to make sure I don't have an extra minus sign that I don't realize is being raised to the 6th power. And so we can see that f of 1 equals f of negative 1, and we're claiming that in general f of x equals f of the opposite of x. And if we were to look at a graph of x to the 6th power, roughly speaking, x to the 6th power has a graph that looks a lot like x squared, but it's growing a lot more rapidly than x squared. And if we take some positive x value and find f of x, then take the corresponding negative x value and find f of x, we'll get the same result. We're seeing a mirror image about the y-axis. So we can also speak of functions as being increasing or decreasing, or increasing on some intervals, decreasing on others. And so I want to take a look at some increasing and decreasing functions. And basically these terms mean exactly what you would think they would mean. So a function is increasing if whenever x2 is larger than x1, f of x2 is larger than f of x1. So an increasing function, again, is just what it sounds like it should be. We have a function that's increasing as we move from left to right. Okay, so for a decreasing function, we have the situation in which whenever x2 is larger than x1, f of x2 is actually less than f of x1. And so I'll draw a rough sketch of something that would be a decreasing function. So here we're just talking about a function that's decreasing, getting smaller and smaller as we go from left to right. And let me just label these for future reference if you come back to look at this again later. So of course the plot on the left shows an increasing function. The plot on the right shows a decreasing function. So let's look at some examples with formulas now. So for example, if we look at y equals radical x, this function, first of all, is not defined for all x values. It's only defined for 0 to infinity. Its domain is 0 to infinity. And here is, roughly speaking, what its graph looks like. And this function is increasing on 0 to infinity. And so let me write that down here. And technically, it's increasing on 0 to infinity, not including 0 itself. Okay. As another example, let's look at y equals 1 over x squared on the interval 0 to infinity. 1 over x squared has two branches to it, but I'm just going to look at the branch on 0 to infinity. And I'll draw, again, a rough hand-drawn sketch of this thing. So a rough sketch of 1 over x squared on 0 to infinity looks like this. And you can see that this function is decreasing. And so I'll note that this is a decreasing function on 0 to infinity. And I just realized I'm going to go back and slightly modify what I wrote on the left. I had put a square bracket next to the infinity, and it needs to be a parenthesis because infinity is not reachable, so we're not including the endpoint. Okay. So as you go through your calculus course, you're going to be working with quite a number of different types of functions. And so I'd like to briefly review what these types of functions are. So a polynomial would look like the following. It would look like a sum of powers of x multiplied by different coefficients. So just as an example, we could have something like 3x to the 5th minus 7x squared plus x minus 2. That would be a polynomial. For a power, there we're simply speaking of a power of x, something like x to the 4th power or whatever. Or maybe we're looking at a negative power of x. Maybe we're looking at h of x equals x to the negative 3rd power. Or maybe we're looking at a rational power of x, like f of x equals x to the 1/2 power. So those would be powers. The trigonometric functions are the 6 trig functions that you're accustomed to. So things like f of x equals sine x, f of x equals cosine x, f of x equals tangent of x, or cotangent, secant, or cosecant. Rational functions are ratios of polynomials. And so an example of a rational function would be something like g of x equals x cubed minus 1 over 2x squared plus 5x plus 3. It's just a ratio of two polynomials. And then exponential functions, of course, would be just built up from exponentials. So things like f of x equals e to the 2x, or h of x equals 3 to the opposite of x, things like that. And then logarithmic functions would be based on logarithms, so we'd be looking at things like f of x equals ln of x squared plus 1, for example, or g of x equals log base 10 of 5x plus 3. So you'll be doing calculus on all of these various different types of functions. Okay, so in these next examples, I'd like to investigate particular functions and just talk through some of the various different properties that we've been looking at here. So for f of x equals e to the x, let me start by putting up a rough graph of this function. So we're looking at exponential growth here. And so here is a rough graph of f of x equals e to the x. Its y-intercept is at y equals 1. And let's just talk through various different properties of this function. So we could talk about the domain of this function. And unless we choose to restrict the domain here, the domain is negative infinity to infinity. We could talk about the range of this function. So those are the y values achieved by this function. Notice that this function never hits 0 and never goes negative. And so the range of this function would be 0 to infinity. We could look for symmetry properties of this function, and this function doesn't have any real symmetry. So I'll just put a note here. There's nothing to comment on here in regard to symmetry. I'll mention that this function is passing the vertical line test. It is a function. And we could talk about it in terms of being an increasing function. And so this function is increasing on negative infinity to infinity. And so that just summarizes how the various terms that we've looked at apply to f of x equals e to the x. As a second example, let's look at g of x equals sine of x. And I already talked a bit about this function, but let's look back at it and look at its domain and range and symmetry and all of that all together in one place here. So I started drawing cosine of x. Let me get a picture of sine of x on here. So here is a rough picture of sine of x. It's supposed to look symmetric, and by hand, just doing the best I can to do a rough picture of it. It gets as high as 1 and as low as negative 1. And so in looking at its domain and range, its domain is negative infinity to infinity. All x values are legal for it. Its range keeps us in the interval on the y-axis from negative 1 to 1. So its range is negative 1 to 1. I'll remind you that the square brackets indicate we are including the endpoints, that negative 1 and 1 are reached by sine of x. The parentheses on negative infinity to infinity again indicate we're not including the endpoints. Infinity is not a number we can reach. In terms of symmetry, I mentioned earlier, I think, that sine of x is an odd function. It's symmetric about the origin. So let me write that down here, that our function is symmetric about the origin, and that it is an odd function. And as far as increasing or decreasing, this function is increasing on various intervals and decreasing on other intervals. So for instance, this function is increasing on 0 to pi over 2. And let me sort of highlight that portion of the graph. So over here, from 0 to pi over 2, this function is increasing. This function is decreasing on pi over 2 to pi. And so that would be this section of the curve here, from pi over 2 to pi. And this function oscillates, and so actually we could say a little bit more about where it's decreasing. It is decreasing on pi over 2 to pi, and in fact it's decreasing all the way till we get to 3 pi over 2. And in fact, if I want to, I can go back and extend the interval on which the function's increasing. It's true it's increasing from 0 to pi over 2, but it's actually increasing from negative pi over 2 to pi over 2. And then we could just continue going from interval to interval, talking about where the function's increasing and where it's decreasing. Okay, so that concludes this tutorial, and we have a couple further examples.